So my name's Steve Horton. I'm a seismologist, which means I study earthquakes or whatever makes the ground move. But in my case, it's earthquakes. And I work at the Center for Earthquake Research and Information at the University of Memphis. I bet you guys know something about the University of Memphis. We're not happy about it. So I wanted to talk to you a little bit about earthquakes in the central U.S. or seismicity in the central U.S. And I thought, and at the same time, I want to introduce you to some products, both that are produced by the United States Geological Survey and that are produced by the Earthquake Center where I work, that promote or will give you information at the time of earthquakes occurrence. And as well, anyway, information is a valuable thing. As it turns out, not every earthquake is going to be the magnitude 8 disastrous earthquake. And just one of the things that you want to know about an earthquake is how big is it and over what area might it actually have impact. So I'm going to start with, generally, earthquakes that happen on kind of an everyday scale, more or less, and work my way up then to earthquakes that happen at a less frequent interval or less likely to happen. So this is a satellite image of the central U.S. Basically, Memphis is down here, the Mississippi River's coming up, Ohio River, Paducah's right around in here, land between the lakes, the Ohio River runs off over here, the Mississippi River goes on up to St. Louis, so this is Kentucky, Tennessee, Illinois, Missouri, and Arkansas. On this image are plotted little yellow symbols, and they're the location of where earthquakes have happened. And in this particular data set, it's earthquakes that happened between 1976, around in there, to about 1997 or so. So almost 20 years of, you just can't get rid of that little thing there. About 20 years of seismicity. So these are earthquakes that are generally somewhere around a magnitude 2. They may be magnitude 1.5. They may go up to about 3 or 4. But what you will see is that there is one area where the earthquakes kind of congregate or actually to define kind of a pattern. And this is what's called the New Madrid seismic zone. Anybody here know something about the New Madrid seismic zone? Yes. Are you mostly, never mind. I was going to ask if you were mostly emergency management people, but I think what I've been finding out is there's a wide variety of people here and a lot of different backgrounds. Anyway, the New Madrid seismic zone is this area here that's very well defined by the seismicity. And generally speaking, it is thought that one of the earthquakes in 1811 happened on this segment of the fault. Another one in January happened on this segment of the fault, and then one in February on the 7th happened on that segment. This particular segment would be the one that helped create Reelfoot Rift, or not Reelfoot Rift, Reelfoot Lake, and to kind of dam for a while the Mississippi River. This is the kind of outline of what's called the Mississippi embayment. The embayment is an area where the coastal plain sediments actually come up into the kind of continental structure. So the coastal plain, the Gulf Coast, which would be down to the southern part of this figure, actually comes into or came into this area when it downdropped at some point in the past. And these sediments actually cause it makes it kind of difficult to study what's underneath. So we can't actually see faults, go out and see them directly because there's a big pile of sediments about a kilometer thick, down at Memphis, more like 600 meters or so here in the New Madrid seismic zone. I would also say that there's a large kind of halo of activity that's very scattered and diffuse that happens in the area to the north and to the kind of west of the New Madrid seismic zone. Over here in this is kind of north central Arkansas, northeast Missouri, and southern Illinois and Indiana. This has been observed for a long period of time, and basically you could expect that there'd be earthquakes more or less any time. In the New Madrid seismic zone proper, we have about 200 earthquakes per year that we locate, that are large enough to locate. That means that they're probably somewhere around the magnitude of 2 or about that, and going on up to about 3. We have very few earthquakes that are actually felt, but we have several each year. And it takes about a magnitude 3 earthquake to occur, and you have to be fairly close to it to actually, for people to actually feel it. If there are any questions, feel free to ask me. I don't mind. This can tend to get a little technical, so if I'm saying anything you don't understand, please ask me to clarify.
How does the Wabash Valley?
Thank you. So this here is the New Madrid seismic zone. There's one other kind of formal seismic zone on this map, which is the Wabash Valley. So the Ohio comes up here and goes off this way, and the Wabash River comes up here. And this kind of general area right here is the Wabash Valley seismic zone. You asked how it fits into it. It fits in general because there have been, if you looked at, and I will show you a little later on, kind of moderate size earthquakes that we've had, the magnitude 5s that we've had in the area since about the 60s, most of them have actually happened in this area, not down here. The largest event that we had, most recent, was a magnitude 5 down at Mark Tree, Arkansas, which is the southern end of this. So there's some things that are structurally similar between this area here, and there's kind of a rifting structure that's under here called the Reelfoot Rift that goes on up and turns and goes this way, called the Rough Creek Graben into Kentucky and on across to the east. And there's a little piece of it that goes up into the Wabash Valley. It's called the Graysville Graben that comes up here a little ways. I'll have more on that a little later. So this is a map that one can get at, that's updated constantly, actually. It's on our website at siri.memphis.edu. And basically it shows recent earthquakes. So earthquakes, and we have a map, we've come out of just looking at the central United States, which would be, that previous map was about this area right here. Now we're looking at a broader area, and we're looking at earthquakes that have happened more or less, well, during the last 6 months. The yellow are earthquakes that happened during the last 6 months. The blue have happened during the last week. And if there had been one that had happened in the last hour, when I made this map, which was like 6 o'clock this morning, then you would see that in red. I'm sorry, I didn't know that I was going to have difficulty, but it's Siri, CERI.memphis.edu. A lot of the information that a reasonable amount of the information I'm going to show you today will be on that web page. So one of the things that you see on this map is that there's certain groupings that actually occur. This right here, Tennessee, Kentucky, Missouri, this little part right here is the New Madrid seismic zone. So as I was saying before, we have about 200 earthquakes a year. So they end up kind of redefining that image that I showed you earlier. There's also that scattering that happens across southern Illinois. This is the Wabash Valley again. I don't know, everybody know when the Mount Carmel earthquake happened? It was April 18th, I think, of 2008. Well, that's an aftershock, or that happened in the same place that event happened, which is just west of Mount Carmel. These are up closer to St. Louis. This is a seismic zone called the Eastern Tennessee Seismic Zone. So it's over in the eastern part of Tennessee, kind of along the Smoky Mountains or the Appalachian Mountains. There's also a seismic zone here, not much activity in Charleston, one in Virginia. This is the largest earthquake on here, is about a 5, I don't remember the exact location or magnitude, it's probably a 5.5. It happens in Quebec. And that's another seismic zone called the Charlevoix seismic zone. Anyway, one of the kind of new areas that are starting to have seismicity, one is over here in Arkansas, in central Arkansas, near Conway. Does anybody know where Conway is? Okay, so just north of there, there's been a lot of recent activity over the last year, really. That has been picking up. And also over here in Oklahoma, this is more or less scattered around Oklahoma City. And there were more earthquakes down here in Texas. These happen to be areas where the gas industry is actually mining for gas or producing gas in what's called the Fayetteville Shale. Fayetteville is actually over here. And they're using a process called hydrofracking. So to create porosity, permeability in that shale layer so that the gas will flow to the wells more easily and they can get it out. And it's a big process in kind of this area of Arkansas and that area of Oklahoma. So we've been yes?
I was under the impression that most seismic areas were where the plates were shifting.
That's absolutely true. But even though that's true that most of it is along the plate boundaries, there's seismicity interior to the plates as well. So we're in the middle of, I don't know if you know, there's something called plate tectonics. Plate tectonics is basically the idea that the Earth is covered by a crust and it's kind of hard. And the basic idea would be that the plates, like the North American plate, which this is part of the North American plate, it goes over the edge of it would be along the San Andreas Fault in California, where it connects to the Pacific plate. So that's why you have a lot of earthquakes there, is the two plates are sliding by each other, and they're sliding by at a kind of constant rate, about the same rate your fingernails grow. And over the course of years, the sides of the fault get hung, and it builds up, and it strains, and it gets more strained, and then finally it overcomes the strength of the rock, and you have a large earthquake. And there are no plate boundaries here. There's one down in the Caribbean, and then there's one way out in the Atlantic Ocean. But they're a couple of thousand kilometers away from us. But nevertheless, we do have earthquakes here. We pick them up all the time. And it just doesn't fit into the model. So anyway, we've been looking recently. So the Center for Earthquake Research and Information, we have three basic objectives, three things we do. One is research. One's public information, which is what I'm doing here now, and the other is monitoring. So we actually monitor, we have a seismic network where we monitor the New Madrid seismic zone. We recently put in 6 stations in Arkansas over the larger area so that we could monitor seismicity in Arkansas. And we're, generally speaking, involved in bringing in a lot of data from the national network through Siri, and it all gets sent back over to Boulder, Colorado, where the National Earthquake Information Center is, which is part of the United States Geological Survey. So if you were to look, if you were to go to our website, a map similar to this would be on our website anytime you go. Another thing that excuse me, I changed the order of my slides. As I had said before, we have a seismic network that we operate. And I just wanted to give you an idea of what it was. Now we've zoomed back in. Memphis is down here. Here's, there's the Boot Hill. So there's Kentucky, Tennessee. We can't quite get up to where we are. But we have a seismic network. All of these triangles are actually locations of seismometers. And the different symbols are also different seismometers. This would be a picture of the ground or the site of one. Basically, they're all solar operated, and so that we don't have to actually power them from a utility. They can be in a quiet place. There'll be a vault, which is, well, there'll be equipment equipment enclosure like those two things there that house batteries and such things as that, and maybe a recording unit. And then there will be a vault. This is the picture of that when you open that top, where the seismometer is actually sitting down in the bottom of it. The seismometers, in that case, is a little can about that big. And basically, it sits there and monitors the movement of the ground. So when the ground moves, the general principle would be that it'd be like you had a magnet that was standing still, and you move a coil of wire around it. When you do that, that motion actually produces a voltage, and the voltage is proportional to what the velocity of that motion is. So it's that kind of physics that we're taking advantage of in this unit here. We digitize that signal, send it out over the radios. It's all sent back down here to Memphis. We gather it all up, and then we look at it, and if there was an earthquake, say right here, the seismic waves would radiate out. And as they do, you can measure by having these stations when that wave arrives at different places. And by knowing how fast the seismic waves propagate through the ground, you can eventually triangulate back to where the earthquake happens. So that's the basic process of locating an earthquake. You can also tell how far away you are. How large the motion was will give you an idea of what the size of the earthquake is. So those are the two basic things we do. We actually have a process in the New Madrid seismic zone that runs continuously and just looks for earthquakes to happen. And one of the other things we do on our website, again, siri.memphis.edu, we have what are called helicorders. And a helicorder is just a display of what that seismometer would be seeing, or how the ground's moving. So this is 15 minutes, each one of these across. And so between there and there are 4 of those lines, so that'd be an hour. And basically it's going along, you don't see a whole lot, but they're little things. The Earth's always moving. And you get down, there's actually a fairly large disturbance here. This is an earthquake. And this is a magnitude 3.9 that was observed on June 2nd, 2005 in Hickman, Kentucky. We have a station there in Hickman. And so one of the things you ought to note from this is we don't often have 3.9s in this area, or else I'd be showing you a more recent figure. This is kind of it's not unusual. I mean, they happen reasonably often. But anyways, so that's kind of what an earthquake looked like. So if you were sitting around your house and you actually felt something and you didn't know what it was, but you thought it was perhaps an earthquake, you could go to our website and you could look. There's a map that'll show you the seismic stations and where they are, and then you can click on that and get a helicorder record near your house or whatever and see if there's been an earthquake. Anyway, I think that's kind of cool. So basically, we're monitoring for earthquakes all the time. I'm sorry, yes?
On that reading, it started very suddenly and then sort of intensity sort of angled up. Is that common?
Yes, absolutely. So that's a very good observation. Basically, the earthquake, when it happens, you have almost nothing. And so whatever happens after that is a big thing. And this one happens to be very impulsive. This record is actually clipped, which means that we're not seeing the whole signal. There's more of it that's up here somewhere. And finally, back here is where you're starting to see what's called the coda. These are waves that come in, the direct waves, the waves that come very on an almost direct path between the earthquake and the seismic station, get there first. The ones that go out and get scattered back, they take longer, and so they lose a lot of their energy. And that's what this is coming in back here. Does that make sense? Probably too much information. Yes?
Does this record local information that's going on too, such as mine blasting?
Oh, yeah, it would. If you walked up next to it, it would record that too. If you drove your car near it, it'll record whatever, if the ground moves, it records it. It doesn't distinguish. But I'm sorry, go ahead.
And you can tell kind of from the style of the,
That's definitely the hope, that you can tell by looking at what we call the waveform, whether it was an earthquake or a blast. If it was a signal, if it was a source that happened close to the top of the earth, there are what are called surface waves that are generated, and the closer you are, the easier it is to generate them. And surface waves, as opposed to happening here, happen back here, and they're kind of long period. So it would look quite different than what it does here. So we monitor, yes?
How deep would that be? Or can you tell from that?
I personally can't tell. It's not shallow because you can't see surface waves. But earthquakes in the New Madrid seismic zone are typically between 5 and 15 kilometers. So it's probably not any deeper, and it's probably, and it's definitely not any shallower. So you can't tell the difference probably from looking at this, but this is from 2008 when the Mount Carmel earthquake happened. It's actually from May 2nd because I was in Santa Fe at a meeting, and I couldn't get back, so I didn't make these figures till I got back. But there's no seismicity here in Arkansas and very little over here in Oklahoma. So I think that's kind of neat. Just in the past the past year really, there's been a lot of activity in these two areas that's kind of taken off. But this is the Mount Carmel earthquake. It was a magnitude 5.2. Prior to that, the largest earthquake in the area was what was called the Southern Illinois earthquake, which would have been kind of right here. And it happened in 1968. That's magnitude 5.4. So this was more or less the same size. The earthquake